Hi again, everybody. Today we're going to talk all about Markov processes, which we just started to define at the last lecture. We'll review the definition if you don't remember what it was. And we're going to try to describe a little bit about how long it takes to get in and out of these states. Remember, it's a continuous time chain now. And so we'll introduce this quantity called the Sojourn Time, and we'll make various different propositions about it. And we're also going to introduce something that's kind of like transition probability matrices. And then we'll finish off with a little bit of a kind of a far-seeing advanced view of stuff that we're not really going to use, but you could use, that are kind of, and you may if you dig further into this subject, that involve sort of the analog of the Chapman-Kolmogorov equations. All right, that's a lot to say, but let's get started. So we'll start today with a review of what we talked about at the very tail end of the last lecture. We gave a couple of definitions. We're starting in on Markov processes, which are continuous time Markov chains. And so let's just look at this little quick review. So these are last time, some definitions we saw. So we just had two. So we had one for Markov process, and then we had one for what it meant for a Markov process to be homogeneous. So the first one was just, what is a Markov process? And this guy is given by some x of t for positive t's or non-negative t's. So that's what we call the process. And it takes on some kind of discrete values. So it takes values in a discrete state space. And such that for any t that's bigger than s, we can make the following statement. Let's move this up a bit. It's a conditional, it's the equivalent to the memoryless statement that we had for Markov chains. So I'll write it out and then we'll kind of discuss it for a second. So it's the conditional probability for x of t taking on some value, and we'll call that value I sub t, and that's a discrete value, but the t parameter is continuous. Given that we have some information about the history, so we'll say x of u is equal to I sub u, but here u can be a bunch of different things. So it's going to be some sort of range going from 0 up to s. Right, so that's the conditional probability that we want to talk about. And so what this is like saying, so this is a probability for the value of the process given some sort of history. Right, so this is the history from time 0 to s. Right, and so what this is equal to, and if you think of it in this way, you might be able to kind of guess. The way it works with Markov chains is that if you know the whole history of the discrete time steps of the chain, it's equivalent to knowing the most recent moment in the chain as a condition. And so that's what it is here too. And so it's the same probability, except the conditional part has changed to just the most recent moment. And so we'll say given x of s is equal to I sub s, like that. And so this half of the conditional statement, this thing here, that's not the whole history from time 0 to s, right? That's just the value at time s. So the gist of this is, look, you probably maybe it helps a little bit, I think, to write this out in kind of words, to kind of drive home the point of what this is saying. It's saying like, so what we're interested in is the probability for the process taking on some value. So we'll write that part is, I'm not going to change that into words. Given some sort of history, so this is just my paraphrasing of the definition. It's not a technical definition. This is the same thing as the conditional probability for the value of the process given the most recent moment in that history. Or maybe most recent value. So in other words, the whole history isn't actually important. It's only the moment in that history that is closest to the time that you're interested in that is important. It's kind of like a cool thing if you think about it in a way. It'd be nice if sometimes it would be nice if that's how the world worked, that it didn't matter what had happened in the past at all. It only mattered where you were exactly at that moment. I mean, it did matter what happened in the past, but given your entire history, that whole past does influence where your current moment is, where your current value is. But it's only that current value that actually plays a role in determining what goes on after that. I don't know, I'm probably mangling that a bit, but I don't know, there's some kind of niceness to it, to me, that I sort of like. So that's the definition of the Markov process. So let's just remind ourselves what we were defining there. So this is the thing we're defining, Markov process. And this thing at the bottom is just my kind of paraphrasing of what that definition is saying. And so we'll move on to our next definition, which we saw at the end of that lecture, which was for a homogeneous Markov process. Which I'll just write as MP for Markov process. So a homogeneous Markov process, and this is the thing that we're defining. It's a little bit different, the statement, than it is for the chain, and it looks like this, so let's just write it out. So it's saying that the probability the probability that x of t is equal to some I of sub t given x of s is equal to some I sub s. The idea of the homogeneous nature here is that it doesn't matter exactly what are the values of t and s, only the difference between t and s is what matters. So that is to say, it doesn't matter when s and t are exactly, it only matters how far away t is from s, or how far away s is from t. And so that's what we're going to say here. So on the right-hand side, this is the same thing as the conditional probability for x at some t minus s having the value I sub t, given that x at some time 0 had the value, I think we have to call this I sub s to make sure that it's the same as the one on the left. There might be a typo in the notes there, if so, sorry about that. And this has to hold for all t greater than s. All right, so that's the definition of a homogeneous Markov process, or in other words, a homogeneous continuous time Markov chain. So I kind of want to emphasize, we're only going to consider these. So I'm going to highlight this. So we only work with or consider homogeneous Markov processes. In this class. So that's probably worth highlighting here. Oops. Just so you remind yourself, in case you dig deeper in the future, that some of these rules we're seeing are only for that case. So that was our review of the two definitions from last time that are important for us now. And so the new stuff starts here. We're going to start with with a new definition and a proposition that we'll prove. So here we go. So this new definition is for something called sojourn time. And so we're going to say that it goes as follows. So suppose you have a Markov process that enters a state I at time 0. So that's sort of how we define time 0, I guess. Right? Then what we call the sojourn time is the time it takes to get out of that state. So the sojourn time and it gets the symbol is W sub I, and it's always greater than or equal to 0, of course, is the smallest time t such that x of t is not equal to I. Right, so it's the first time at which you get out of that state. Yeah, and so we call that the sojourn time, so that's our definition here. All right, and then we'll make a little proposition about the sojourn time that sort of gives it a kind of a memoryless quality. So we'll say, here's our proposition. This is a kind of an analog of memoryless. So we'll say that the probability that the sojourn time for state I is greater than some s plus t, given that it's greater than t, or sorry, greater than s, is the same thing as the probability that it's greater than t. Right? So you should think about that for a sec. So it's saying, so if you're asking what is the probability that the sojourn time is bigger than, you know it's bigger than s, and you're saying, what is the probability that it's bigger than s plus this extra bit of t? Well, that's the same thing as saying that it's bigger than t itself. Yeah, and so that's the proposition, and we're going to go ahead and do a proof now. All right, so here's the proof. So this is the proof of this, in a sense, the memoryless nature of the sojourn time. Right, so the idea is we'll start with the usual setup. The x of t is a Markov process, and we'll suppose that you've fallen into state I at time t equals 0, the same setup we've been using the whole lecture. And so we're just going to take apart the left-hand side here. So we'll say the probability that wi, the sojourn time for state I, is greater than s plus t, given that it's greater than s. All right, so we're going to kind of disassemble this here, kind of write it out in detail. Like, what does that statement really mean? So what it means is the probability that x of u is equal to I for u in the range 0 up to s plus t. right? Given that x of u is equal to I for u in the range 0 to s. All right, so that's just what that left-hand side says, just kind of rephrased in a way. And then we can tidy this up a bit. There's some sort of redundancies here. So if you look at this saying, it says that x is in the state I for all the times going from 0 to s plus t, given that it's in the state I for times 0 to s. So the fact that this is 0 to s means that most of this time is redundant. We don't need... So in other words, a lot of this is already given in this conditional part over here. So let me just write out what I'm trying to say here. So this is the same thing as the probability that x of u is equal to I for u in the range s to s plus t, given this same half over here. Right, so there's nothing that's really changed there. I've just kind of gotten rid of the redundancy in the statement there. All right, and now we're going to use the memoryless property because to sort of shorten this bit over here. Because again, the fact that this is a Markov process means that this conditional statement here, it's not the whole history that matters. It's only the most recent moment in the history, right? So let's just copy that down, put it over here, and then I'll sort of work by erasure. I've been doing that with the memoryless stuff for a while. So we'll erase this stuff here, and we'll say this. Close this off, and we'll say like that. Right, so that's just by the memoryless property. And then we're going to use the homogeneous property. And that says that, remember that s and t don't really matter so much as the difference, the distance between the two. So we may as well just put s equals 0. That's perfectly fine. And so we get thing we were trying to prove, right? That's the sojourn time being greater than t. Right, so that's our little proof for this guy. So we should stop just for a second and think about what it is we've just shown. So this property up here, I should probably put this in words again. This is famously actually called a memoryless statement. So this means W, the sojourn time, is memoryless. You sometimes hear that phrase in this class used in different ways, but this is a version that's quite common. You might have seen it in some of your other classes already, actually, that version of the statement. And it turns out that the fact that this parameter, the sojourn time, which is like a random variable here, is memoryless, tells us what its distribution is, because it turns out. So this is just written as kind of a claim in your notes, but so I'm just going to say it. So the claim, what we've just shown here, means that Wi follows an exponential distribution. With parameter, we'll just put in some parameter. It has one parameter. And the reason for this, so the reason is because the exponential distribution is actually the only continuous how do I say this? It's the only continuous memoryless distribution. Sometimes people write this like this. But I don't know, I kind of don't like that because it reminds me of the operator, like e to the something, but in any case. Continuous and memoryless distribution. You can certainly show easily, I think. And so if you don't remember, this means that the PDF, so WI's PDF is the following. So we say, how do I write this? F of t is equal to, with an I guess we should put underneath it, is equal to, I guess you do it in this piecewise way. So it's lambda sub I e to the minus lambda I times t for t greater than or equal to 0. And then otherwise it's 0. And so, oh, I missed a piece there. Yeah, so that means this is the PDF for the thing. It's easy to see that this PDF means that the exponential distribution is memoryless. You could just try it out. But it's not so easy, I think, to show that memoryless means this is the PDF. So I looked around for a proof. There's no proof in your notes for this. And I'm sure there are lots of proofs out there. I'm sure you can find many of them. But you can find the one I found if you want. It's in a book that's not on our reading list or anything. But you can see proof in, it's a pretty nice book. It's a book by these guys called, two different guys, Grimmett and Sturzaker. They have a book called like 1,000 Exercises in Probability. I think it's in that one. And it's 1,000 exercises. In probability. It's a nice book. Any kind of problem book is usually pretty good. There's just good practice. 1,000 exercises in probability, and I think it is in part 4.14.5. If you want to dig that up, it's probably in the library. You can buy it too. It's not very expensive. I think it's a paperback. It's like 20 pounds or something. But yeah, it's a nice book. And you can find the proof in there. We're not going to show it to you here. But going, again, like I said, going one way is simple. Going the other way is a little harder. All right, so we're now going to introduce another couple of definitions. So we're going to introduce something. We're going to have a little bit of a redundant notation here. So it's a definition. And we're going to define Pij for a Markov process. I should write that above that. So for a Markov process, Pij is equal to, it's the probability that a transition from I, how do I say this? That you transition from I to J, given that you actually transition away from I, right? So this is in words. This is the probability that you transition from I to J, given that you actually do transition away from J. or away from I rather. Okay. And in our notation, we can rewrite that. All right, so for us, same thing as rather just says that Pij is equal to the probability that x at the sojourn time, so that's the time it takes to leave state I after you've arrived at state I at time 0, that's given all of our conditions, is equal to state j. Right? And just a couple of things to point out. So notice what should be the value of Pii? If you think about that for a second while I tidy up. That means that what's the probability of going from state I to state I given that you left state I? And that maybe makes it sound a little confusing, but if you think about the sojourn time, that's the time that it takes to leave state I, and by definition, in the sojourn time, that means you're no longer in state I. And so this is 0. And another thing that's important to notice is that if you sum over j, so for all the j's in the state space, I'll just leave that as kind of understood, of Pij, you get 1 for all the different i's. Okay, so that's the, I don't know if I have a name for this exactly, it's this guy that we've defined. It's sort of like, well, you'll see in a minute, it's not exactly the same thing. It's not our exact analog of the transition probability matrix. There's something that's a little better for that. So the notation is a little unfortunate because you'll have to judge from context if we're talking about a continuous time process, a Markov process, rather than a chain. All right, so we got one other definition here. And this, this is sort of, for every time you create a Markov process, the time parameter is continuous, right? But you could imagine just sort of ignoring that and thinking about the collection. You could make like discrete times and label, like let's say you're in state 1 for 3 days, and then you're in state 2 for 24 seconds, and so on. You could just eliminate all those continuous time variables, values, and name those segments like time 1, time 2, and so on. And you could produce a Markov chain. So there's something that's called like the embedded Markov chain that comes along whenever you invent a Markov process or whenever you have a Markov process. So we'll name that. So the process y sub n such that n is equal to 0, 1, 2, and so on. Where y sub n is, how do I write this as? Is the state of xt after the nth transition. So we've sort of blocked our times into, or sorted our time into blocks, each of the different sojourn times or whatever. So this process is the embedded Markov chain. So you get one of these, every time you have a Markov process. It's just like you say, okay, discretize the time. And so that's what this guy is, the embedded Markov process. Or sorry, the embedded Markov chain. So you might see in your notes, there's a proposition, I think it's proposition 5.1, that's somewhat detailed, and it relates the stationary distributions for the Markov chain or the Markov process and its embedded chain. And there's an interesting, simple relationship between the two. But I'm going to skip that, so we'll have that be non-examinable. So I think that's proposition 5.1, if you want to make a note of that for yourself. So the next thing we're going to do is we're going to show you a proposition that we'll prove. Always more fun, I think. So it's a proposition. It's also kind of a definition. Well, I guess the definition, we'll write that separately. I think in the notes, they're all kind of buried together. But the idea is this. So suppose you have a Markov process x of t. So for Markov process x of t with sojourn times so w sub I obeying an exponential distribution with parameters lambda sub I and with pij as above. As above, so I better scroll back there. Look, that's this guy over here. I didn't give a name to this, but the probability, it's sort of like a transition probability. So for these guys, we can make the following two statements. So the first one is, so these are going to be limits. So the limit as time goes to 0 of the following ratio. So the probability that x of t is not equal to I, given that x of t is equal to I, divided by t. This is actually equal to lambda I. So that's one of the parts. And the other part says same limit, t going to 0, for the probability that x of t is equal to j, given that x0 is equal to I, divided by t. This guy is equal to lambda I times pij. And that's for I not equal to j. Right? So that's our proposition. And we're gonna prove that, but just I'll give you a quick definition here. These symbols collectively, so I don't think this is given as a definition in the notes, but it's useful this way, I think. These guys collectively, so lambda I and the product lambda I times pij, these guys are called transition rates. And so that's just the name of these guys. All right, so now we can work on the proof of that. So here's the proof. So we're just going to work on this in a straightforward way. So we're going to take on the left-hand side. So the probability that x of t, so this is for part 1, is not equal to I, given that x of 0 is I. So think about what this means. So I'm going to claim that this means this is the same thing as saying the probability that wi is smaller than t. Right? Because according to this, you're not in state I, but you were at time 0. So it must mean that time t is larger than a sojourn time. Okay, and so this is equal to, since we know the distribution, we know that the sojourn times have an exponential distribution, this is just equal to the integral from 0 to t. Sorry about that. Over time of lambda I e to the minus lambda I times t. And then that integral, you can do this as simple integral. So this is 1 minus e to the minus lambda I times t. You can evaluate that integral. And now we're going to do a Taylor series on the exponential here. And so this is 1 minus, because the Taylor series is going to have a 1 in the front of it. 1 plus minus lambda I times t plus 1/2, or I guess 1 over 2 factorial minus lambda I times t squared, and so on. This is just the exponentials Taylor series, right? And then when you take out the 1, what you're left with is just this guy, so minus lambda I. Let's see, isn't there a minus sign in front of this? Let me think for a second. Let's get rid of the minus there. Lambda I times t. And then let's just leave the minus signs in front now. Gets confusing trying to keep track of them, I think. And I'll just leave the dots there. And so that's what this thing looks like, the left-hand side. But what the idea, remember, is to take that left-hand side and divide it by t. Right? And then take the limit. Right, so this is then lambda I minus 1 over 2 factorial. And then how does this look? So this is going to be minus lambda I squared times t plus dot dot dot. And all those future terms have like t squared and t cubed, and so they all have some power of t there. And we want the limit that t goes to 0 it's kind of squeezed there. And so that's clearly just lambda I, right? So that's the first part of the proof. All right, the second part's pretty different. So we're going to say, suppose that we've got I not equal to j. We're going to basically use a bunch of conditional probability statements here and kind of rearrange them. And then we'll take the limit at the end. And then, so what we've got is the following. So the probability that x of t is equal to j, given that x0 is I. That's a conditional probability, right? So we can write that just using the definition of conditional probabilities and say, so this is the probability that x of t is j and x of 0 is I divided by the probability that x of 0 is I. Right, so that's just a conditional probability. And then if you remember, I is not allowed to be equal to j. Right, so if that's true, I can just insert the following. So I can write this top thing as, I can write that joint probability as the probability that x of t is equal to j and that x of t is not equal to I. And that x of 0 is I, right? Because this is exactly the same, because it's already the case that I is not equal to j, so that's fine. So this divided by the probability that x of 0 is equal to I. All right. And now I'm going to take that joint probability and write it as a conditional times a joint. So let's see what I mean here. So this is the probability that x of t is equal to j given the second half times, how do I write this? The same. Does it fit there? Maybe not. See if we can move everything over a bit. Just in case. All right. And then the denominator is the same. But if you look at this, so these guys collectively, right? So that joint probability at the top divided by that probability at the bottom, that's another conditional probability statement, right? So what we've got is, so I'll steal this long one. Times this joint, or this conditional statement. Which should look familiar from the last proof, or the last part of the proof, right? But so let's just think about these different pieces here. So over here on the left, this guy, this thing here, x of t is equal to j. That just means you had a transition from I to j, right? And this piece here, right? Oh, sorry, let me rephrase this. So this thing on the left means you transition specifically from I to j, and this bit here means like transition occurred. Means you left I, you left state I. And then that last one is saying that you were in state I at time 0. And so all that stuff at the beginning here, this whole first term, this is Pij. And then, so we bring this guy over here. Like that. All right, and so therefore the limit, which is what we're interested in, of, where do we have it? This quantity here, let's grab it, divided by t, it's equal to Pij times the limit t goes to 0 of, well, I could take it from here, right? But doesn't it look familiar? Isn't that the previous thing we were proving? Right? So that's lambda I. Right? And so therefore we have that this thing is equal to Pij times lambda I, which is what we were trying to prove. All right, so let's try to put these rates together. So it's pretty common actually to put the rates, the lambda i's and the lambda i's times Pij into a matrix. So we're going to do that here. So we're going to define a matrix of these things. And it has a fancy name, but so let's say, so the matrix, so we'll call it Q, and it has elements Qij, where Qij looks like this. So it's lambda I. This is sometimes easier to express the elements than to write out the whole matrix, times Pij minus the Kronecker delta ij, like that. Right, so if you want to look at how this looks written as out as a matrix, you can do that too. It looks something like this. Oh, so how does Q look? So the first, let's just look at the first row. So the first row, when I and j are both 1, that's delta ij is 0. So we just get lambda I times pii, or sorry, how does this go? I've said this wrong. The pij is 0. The delta ij is 1. So we get minus lambda I. Get myself all tangled up. And then the next element is lambda 1 p1 2. The next element is lambda 1 p1 3, and so on. And then the next row would be lambda 2 p1 2 minus lambda 2 lambda 2 p, hang on, I've got this wrong. Wrong. 2 1 2 3, and so on. And you can look at all this. You can build up this matrix like this. This is the same as above. So there's along the diagonal, there's minus lambda i's, and then the off diagonal are these other rates, the products of the lambdas and the p's. This thing has a name, so this is called, it's kind of a long name, infinitesimal, I don't know how to spell infinitesimal, hope you do, infinitesimal generator matrix. We don't really care about its name, but you might care. I don't know. That's what it's called. People call it this guy. So that's just the definition of this guy. It's kind of really useful. We're not really going to use it so much, but it can be used a lot. So it turns out this is the analog, the Markov process analog or counterpart of the one-step transition probability matrix, right? So I'm just going to make some comments. So note or comment or remarks. Remark, that sounds like a math person. Right, so here are the remarks. Q is the Markov process counterpart in some sense of a one-step transition probability matrix. Right, so that's just a sort of a bold statement. I'm not really telling you what it is. The QIJs are, I think, pretty clearly not probabilities, because some of them are negative. So they're not a bunch of probabilities. Also, it's true that if you sum down the column, so sum over j, qij, these sum to 0. These things have a lot of information about the rates and all sorts of stuff. But so here's the idea. So what happens is you can build this matrix. So you can make the following. So this is sort of far seeing into the future. We're not really doing much with this, or we aren't going to use this, but I just want you to see it. You can make the following thing. You can make this P with a superscript of T. If you define that to be e to the t q, which might bother you, I don't know, have a matrix in an exponential like that, but you can define that using a Taylor series, right? So this guy, you can just define this as sum over n, what do I want to use? K, sorry. T to the k over k factorial. And then you've just got powers of the matrix here. Maybe you all know about that. But anyway, so don't worry about matrix in an exponent like that, big deal. This is the matrix that contains probabilities of transitions between states in some time t. Big deal, I don't know what that means, but this is the matrix that has an analog of Chapman-Kolmogorov equations. obeys the following, things like this. Chapman-Kolmogorov equation lookalike. So this is P m plus n is equal P to Pn times Pm, and so on. Just wanted to show you that because it's kind of cool. Maybe you're going to dig a lot more into this subject and you'll use this a bunch. I don't know, but I thought you should at least see it. All right, so that was a whole lot about Markov processes and just kind of getting started with them and seeing some of the things we might be able to talk about with them. And that'll be all for today. And in the next lecture, we'll introduce a particular type of Markov process and we'll start dealing with it. Until then,